Hi friends, welcome to my channel. Before going to the video, those who are not subscribed our channel, subscribe it and also click the bell button. In this video, we are going to see about Norton's theorem. It is the dual of Thevenin's theorem. It is an analytical method used to change a complex circuit into a simple equivalent circuit consisting of a single current source in parallel with a resistance. This theorem states that a linear two-terminal network consisting of several current sources, voltage sources and resistors can be replaced by a single current source in parallel with a single resistor. The single current source is known as Norton's current and the resistor is known as Norton's resistance. This Norton's theorem is useful to solve problems on parallel generators with unequal EMFs and unequal impedances. This theorem can also be interchangeably used with Thevenin's theorem through proper source transformations. In Norton's theorem, the first step is we have to find the Norton's resistance. For this, we have to identify the target element across which the Norton's resistance has to be determined. And after identifying it, we have to remove the target element and find the equivalent resistance by removing all the power sources in the original circuit. Voltage sources are short circuited and current sources are open circuited. Suppose if any internal impedances are given, they are replaced by their internal impedances. That is, the voltage source and current source are replaced by their internal impedance. So this equivalent resistance is known as Norton resistance. This Norton resistance is equal to the Thevenin resistance. Both will be same. Next step is to find the Norton current. For this, we have to identify the target element and short circuit the terminal of the target element. After short circuiting it, we have to find the short circuited current through the target terminal. And this is the Norton current, and this current will be equal to Thevenin's voltage by Norton's resistance. And one important thing you have to remember is that if there is no independent source present in the network, then the Norton's current is equal to 0. Let us understand the Norton's theorem by using a problem. So the problem is find the current I using Norton's theorem. Here the current I is the current through the load resistor RL, which is equal to 5 ohms. The independent voltage source is 30 volt. Independent current source is 2 amps and the resistor values are R1 is equal to 3 ohms, R2 is equal to 3 ohms and R3 is equal to 3 ohms. The options are A 1 amps, B 4 amps, C 2 amps, D 5 amps. The answer is C 2 amps. Let us see how we got this answer. First step to find the Norton's equivalent circuit is to find the Norton's resistance. For this, we have to short circuit the voltage source and open circuit the current source. And also we have to remove the target element. So after removing all this, if you see the circuit, resistors R1 and R3 are in series and their equivalent is in parallel with resistor R2. So Norton's resistance is R1 plus R3 parallel with R2. R1 plus R3 is equal to 6 ohms parallel with 3 ohms. So 6 into 3 divided by 6 plus 3, which is equal to 18 by 9. So Rn is equal to 2 ohms. This Norton resistance is same as Thevenin resistance. The next step is to find the Norton's current. To find the Norton's current, first we have to find the Thevenin's voltage. For this, we have to open circuit the terminals across the target. After open circuiting and applying Kirchhoff's current law, we have Vth minus 30 divided by 3 plus 3 plus VTH by 3 is equal to 2. Here the entering current to the node is 2 amps and the leaving currents are VTH minus 30 by 3 plus 3 and VTH by 3. So according to Kirchhoff's current law, entering current 2 amps is equal to leaving current. So simplifying, we have VTH is equal to 14 volt. Now we know that Norton's current is Thevenin's voltage by Norton's resistance or Thevenin's resistance. So IN is equal to 14 by 2, which is equal to 7 amps. So Norton's current is 7 amps. The next step is to find the current through the load resistor by using Norton's equivalent circuit. So the equivalent circuit is nothing but current source whose value is 7 amps parallel with resistance which is equal to 2 ohms and the load resistor is 5 ohms. The current through the load resistance can be calculated by using current division rule. So I is equal to IN into RN divided by RN plus RL, which is equal to 7 into 2 divided by 2 plus 5, which is equal to 2 amps. So current through the load resistor is 2 amps. Now let us see the previous year's questions. The first question is, a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source in parallel with resistor Rn, where Rn is the ratio of. Here some options are given and this question was asked in June 2014. First option is closed circuit voltage to the short circuit current at the terminal pair, open circuit voltage to the open circuit current at the terminal pair, open circuit voltage to the short circuit current at the terminal pair, closed circuit voltage to the open circuit current at the terminal pair. We know that the resistance, Norton's resistance or Thevenin's resistance is equal to open circuit voltage to the short circuit current at the terminal pair. So only option 3 is correct. Next question, which equivalent circuits are dual? This question was asked in December 2014 and the options are Norton Thevenin, Thevenin superposition, Norton Thevenin and Norton Millman. So the correct option is Norton Thevenin's. These two are dual because in Norton's we have current source in parallel with resistance and in Thevenin's we have voltage source in series with resistance. Next question is match the following. This question was asked in June 2015. First, superposition theorem. We know that superposition theorem is applied only to linear circuit and not to non-linear one. So the option is fourth option, not valid to power of the circuit because power is a non-linear quantity. Next, maximum power transfer theorem. Maximum power transfer theorem, maximum power is transferred when the load impedance is complex conjugate of internal impedance or equivalent impedance of the circuit. Norton's theorem, we already seen that ideal current source in parallel with resistance. Next, the reciprocity theorem states that ratio between voltage and current is constant in different loops. So option C is correct. Next question is assertion and reason type, and this question was asked in July 2016. First, the assertion is any two terminals of a network composed of linear, passive and active circuit elements may be replaced by an equivalent current source and a parallel resistance. The reason is a current source always delivers constant current irrespective of the particular configuration of the circuit to which it is connected. So here both the statements assertion and reason are true and reason is the correct explanation of the assertion. So the next question is, consider the following statements This question was asked in November 2017. So the first statement is Telighan's theorem is applicable to any lumped networks. Lumped network means this network contains physically separable elements, that is R, L and C are physically separable. They are not distributed in the network. And second one, reciprocity theorem is applicable to linear bilateral networks. Bilateral network means the elements in the network conduct current in both the direction. There are bidirectional elements are used. For example, resistor, it is bidirectional. Current flows through both the direction. And next is, so both the statements are true, and the third statement is Thevenin's theorem is applicable to two-terminal linear active networks. So this statement is also true because it is applicable to linear active network only, two-terminal linear active network. And next one is Norton's theorem is applicable to two-terminal linear active network. So this statement is also true. So here the option C is correct. Thanks for watching the video. For more videos, don't forget to subscribe our channel.